An internal jet is formed, much as in the case of the missile entry cavity. The velocity of the jet is very high. The impact of these jets on a surface can produce high stresses. Here, a bubble collapses near a photoelastic specimen. The close spacing of the fringes indicates the very high stresses that are induced. Clearly, jet impact is another mechanism which may account for severe damage. There is an important parameter which describes the conditions for cavitation similarity and is the basis for scaling of cavitation phenomena and model experiments. This is the cavitation number sigma. P sub A is the ambient absolute pressure, P sub C is the cavity pressure, rho is the mass density of the liquid, and U is a reference speed characteristic of the flow. The cavitation number at which inception of cavitation takes place is called the critical cavitation number. Above the critical cavitation number, no cavitation occurs. Below the critical, it does occur. Operation with a cavitation number well below the critical produces a very large cavitated region. In two-phase, one-component flow, the cavity pressure is just the vapor pressure. In a multi-component flow, the cavity pressure is the sum of the partial pressures of the vapor of the liquid and of any gases that may have been introduced into the cavity. In fact, a cavity developed entirely with gas from an outside source behaves and appears very much like a cavity formed by means of the vaporization process we have been discussing. To illustrate this point, we will compare this vapor cavity with an air-filled cavity. Air at near atmospheric pressure is being introduced through the sting into the wake of the disk. Its envelope looks very much like the vapor cavity we have just seen. We formed this air cavity, or ventilated cavity as it is called, by operating the channel at a low water speed and high ambient pressure. To form the vapor cavity, the channel was operated at a much higher speed and under considerably lower pressure to obtain approximately the same cavitation number. The size of the physical system being studied does not appear in the cavitation number, but it is a factor in the Reynolds number. Consequently, as long as Reynolds number effects are taken into account properly, cavitation similarity requires only that the cavitation number be the same for the prototype and for the model. We see that a model experiment can be made at lower speed than that at which the prototype operates if we simultaneously reduce the pressure under which the model is operated. The operation of the cavitation tunnel is based on this principle. We have seen what cavitation looks like, have learned about some of its effects, and examined some of its features as it develops. Pressures near the vapor pressure requires the presence of nuclei, which contain minute amounts of vapor, gas, or both. Cavitation will occur only when these nuclei become unstable and grow when subjected to a pressure reduction. The conditions for such growth can be derived from an analysis of the static equilibrium conditions for a spherical nucleus. The internal forces produced by the partial pressures of the gas and vapor within the nucleus must be balanced by the ambient pressure and the surface tension pressure at the nucleus-water interface. Thus, the condition for static equilibrium is that the ambient pressure plus the surface tension pressure equal the vapor pressure plus the gas pressure. We've plotted this equation for a nucleus with a particular gas content. The pressure adjacent to the bubble has a minimum value which is below the vapor pressure of the liquid. As long as the ambient pressure is above this minimum, and the initial bubble radius is smaller than the radius associated with it, the nucleus is stable and tends to reach an equilibrium radius along this portion of the curve. If, however, the pressure drops below the critical value, the bubble becomes unstable and grows without bound. If a smaller gas content is available, even lower pressures are required. Now let's look at an experiment performed by Ellis to illustrate this behavior. We are looking just below the water surface in a tube which has been evacuated to near vapor pressure. Near the bottom of the tube, out of sight, small nuclei of the order of 5/1000ths of an inch are formed by evolving hydrogen from one platinum wire and oxygen from a second wire by means of an electrical impulse generator. The bubbles are unequal in size, the hydrogen bubble being the larger. As they rise toward the free surface into regions of lower hydrostatic pressure, the larger hydrogen bubble reaches critical size and grows explosively, while the other does not. Although the smaller oxygen bubbles expanded as the pressure was reduced, they never reached a size large enough to become unstable. On the other hand, some of the larger hydrogen bubbles, which moved along a curve such as this one corresponding to a larger gas content, did expand to a size large enough to slip into the unstable region and grew explosively. Bubbles represented by the portion of the curve to the right of the minimum point are already unstable and cannot exist unless stabilized by some external mechanism. Now, even a stable nucleus can decrease in size and eventually disappear because its gas content may diffuse into the surrounding fluid. We can show this with the Venturi experiment by comparing the cavitation inception pressure for freshly drawn water with that for water which has rested undisturbed for some time. Because the discharge is to the atmosphere, increasing the driving head increases the velocity and thereby reduces the static pressure at the throat. This bucket is freshly filled with tap water. As we raise the bucket, cavitation begins at a head of about 2 feet and continues to develop as the head is further increased. We will now leave the water undisturbed for an hour, then repeat the experiment. As we start the flow again, there is no cavitation at the 2-foot head. With the settled water, a much higher head is needed for inception of cavitation, about 3 feet. During the settling period, some nuclei could rise to the surface and vent if they were very large, and some could decrease in size by diffusion of air into the surrounding water. Consequently, a greater pressure reduction was required to cause cavitation in that sample. What we have just seen leads to a dilemma. Nuclei in mechanical equilibrium disappear through diffusion of the gas into the surrounding liquid. Unstable nuclei cannot persist. Yet we have seen that nuclei must be present for cavitation to occur at pressures near vapor pressure. How then can we account for the persistence of nuclei? We must conclude that some external mechanism is required, such as entrapment of gas in the crevices of solid boundaries or on dust particles which contaminate the liquid. We do not fully understand all of the mechanisms of nucleation, and yet such understanding is very important to the prediction of performance either a priori or from models. Many basic aspects still remain to be explained. Nevertheless, we do know a great deal about cavitation, and its effects on performance of machines can be predicted fairly well when cavitation is unwanted, when it is inevitable, and when it is sought.